students, and welcome to Halloween Demonstration Day. You're going to see a variety of chemistry demonstrations throughout this video that are going to illustrate a bunch of different types of chemical reactions and processes in chemistry. Now, some of these things you may already be familiar with, and others may seem completely new to you and you just haven't gotten to this part of your study in chemistry yet. That's okay. If we use some vocabulary that you're not familiar with, just sit back, listen, enjoy, and try to take in as much as you can. Your teacher may give you an assignment to do after watching the video, but nothing would be to the extent that you would need to take notes or write anything down as you're watching. So just enjoy the demonstrations, learn a little bit of chemistry along the way, and happy Halloween from the chemistry teachers at Conestoga. So we're going to start out with this first demonstration. You might have been wondering why during that introduction. And by the way, my name is Mrs. Alvarez, and I'm a chemistry teacher on the second floor at Conestoga. Why I had this silver-looking bottle in front of you while I was doing the introduction. So this is my bottle that I spent a lot of time over the past 6 weeks while you were at home learning virtually, collecting ghosts of chemistry students past. Conestoga has been a quiet, eerie place for a long time since our shutdown back in March. And it's given me plenty of time to, just like Ghostbusters, spend hours upon hours from hallway to hallway collecting ghosts and trapping them here in this bottle. So now that we're converting back to hybrid instruction and we're slowly filling up the hallways of Conestoga, I thought this was a perfect time to let those ghosts out. So be careful when and if you make your way back here, watch out for those ghosts. You want to be paying attention right here to the mouth of the bottle. Okay, so what happened in this particular chemical reaction? Well, little did you know, and I have to be real careful when I do this bottle is very hot. So excuse me for a second while I grab a paper towel so I can show you what was inside. By putting just regular old household tin foil around this bottle, you weren't able to see what was going on inside of here. And this bottle, like I said, is very hot at this point to the touch, to the point where it's tough for me to even get this off without getting my fingers. In chemistry, we call that an exothermic reaction, a reaction where heat exits the system. Very, very warm. And I'm going to hold on to the top of this here so it doesn't spill over on us. But you can also see now that I've pulled it off that you really can't see inside of the bottle because there's so much steam as well as some of that vapor that's left behind. So what was inside this bottle? In the bottom of the bottle, I had some highly concentrated hydrogen peroxide. So it's the same chemical that you have at home in the brown bottle in your medicine cabinet, but a much higher concentration, a chemist level strength. And then inside it, little did you know, I didn't just have the stopper. I had a little packet of manganese dioxide trapped to the side. And so when I pulled the stopper, the packet fell down into the peroxide, allowing the two reactants to mix and the reaction to take place, which gave off a tremendous amount of energy, hence the heat, vaporizing a lot of the water and creating what looked like smoke from the water vapor, but that was really the oxygen gas that was leaving. So oxygen gas is normally colorless. We look around the room, we can't see the oxygen gas, but because of so much heat, it created a lot of steam from the water that was there and mimics looking like smoke. If you were here, it doesn't smell like smoke, okay? It really is just water vapor. So that's an example of the first reaction, and it's actually a decomposition reaction. The manganese dioxide is what's called a catalyst, something that speeds up a reaction, but isn't a direct reactant or product. And the single reactant was the hydrogen peroxide. And then it broke apart into oxygen gas and water, thus the steam that you see. Thanks.
Hi students, I'm Mrs. Roberts, another chemistry teacher from the second floor, and we're going to do a little bit of a twist on that demo that you just saw. So what I'm going to do is I'm going to call this our oozing pumpkin. So I'm going to take some hydrogen peroxide, and as Mrs. Alvarez mentioned, it does always come in these dark bottles, whether you're buying it in the store, which is about 3%, or if you're using lab grade, which I have here, which is about 30%. So it's much more concentrated. Now, why does it come in this accordion style bottle? It comes in this accordion style bottle because one of the products of the reaction, as you may remember from that first demo you just saw, is a gas. And if we are producing a gas in a sealed bottle that has no room for expansion, then we obviously are going to have a problem, and this could potentially explode. We actually had this happen in the chem stock room a couple of years ago, and it was not good. So hydrogen peroxide is a colorless solution on its own. You're seeing it right here. I am wearing gloves because this is very caustic when it's this concentrated. Burns your skin a little bit. It's not very pleasant. All right, so I'm gonna take our hydrogen peroxide. Now, if I let this sit here, it is light sensitive, that's why it's in that dark bottle. If I let this sit here, eventually it would decompose into water and oxygen gas, but it would take a really long time. So we're gonna catalyze it and add some secret ingredients here to make it a little bit more entertaining. Now, I'm gonna add some blue food coloring purely just for visual effect. It has really no effect on the chemical reaction. I'm gonna stir that up here just to get some nice blue foam here. That'll be the goal. Now I'm gonna put that here inside my pumpkin. Now, in this case, we are still going to catalyze this reaction, but instead of using manganese dioxide, which is a solid catalyst like we did in the last demo, we're going to use potassium iodide, which is an aqueous solution. So, I'm going to put that here, measure that out. And again, this catalyst, all it does is it essentially kickstarts the reaction. So it's going to make this decomposition reaction happen much, much faster, okay? Now, before I add my catalyst, I'm going to add one secret ingredient, but I'm gonna tell you what the secret ingredient is. Our secret ingredient is soap. Now, why am I adding soap? Well, we're trying to make some foam here out of our pumpkin mouth and nose. So adding the soap is going to trap, hopefully, that oxygen gas as bubbles and create this foam. Just a little bit more just to be safe. We want to get some nice good foam here. All right, so before I add our catalyst, do need to say the magic words. So I should have the proper attire. All right. Double, double, toil and trouble, fire burn and cauldron bubble. All right, here we go. Now, you may not be able to see necessarily in the video, but there is a lot of steam coming off of this, which should tell you once again that this is a very exothermic reaction. So it's giving off a lot of heat. You can see our foam here. And again, it is just sort of bubbles there, and what's happening is that oxygen gas is trapped in the bubbles, or excuse me, is trapped in the soap, creating those bubbles, and we get this nice foam effect. Now, even the foam is very, very warm to the touch. Remember, I have gloves on. That's the only reason I'm allowed to touch this currently. I did cover up the top, otherwise it would have shot out of the top as well. If you're curious about other sort of versions of this demo, this is often also referred to as the elephant toothpaste demo, and if you do that in a large graduated cylinder, you kind of get a giant toothpaste effect. So that is just another variation on our hydrogen peroxide decomposition. Thanks for watching.
Hello, I'm Dr. Mihalsik, and I'm here to show you a couple of demonstrations. This one you've seen a variation on already. So I'm going to take some concentrated hydrogen peroxide. I'm going to put it in this very large graduated cylinder. And as you can see, not much happens because hydrogen peroxide decomposes very, very slowly over time. So it just looks like nothing's happening. Well, let's make it interesting and speed it up a little bit. Oh, let's not have that fall over. I'm going to add some dish soap so we can see some bubbles. Still nothing happening. And also I'm going to add some food coloring just for color. So let's get it a fun color. Still nothing happening. Well, let's speed this reaction up. It's a very, very slow. Let's add a catalyst. I'm going to add potassium iodide. So as I add the potassium iodide, you can see some bubbles are starting to form here. The reaction is releasing oxygen gas. The oxygen gas is being trapped in the bubbles. It's coming out of the graduated cylinder. And let's see if we can test it and see if it is indeed oxygen. So I'm going to take a burning splint. See if I can ignite the oxygen. I don't know if you can see that, but the oxygen that's coming off the surface is indeed igniting here. So the splint is burning more and more intensely as it encounters the oxygen. Oh, there we go, I got some reignition there. It's hard because the bubbles themselves have water in them, so they're smothering the flame. But I think you got the idea with the reignition. That's caused by the oxygen. Another name for this is elephant toothpaste, because it's a very, very big volume of stuff. It looks foamy, just the amount of toothpaste an elephant should need.
Hi students, I'm Mrs. Showers and I'll be demoing our next Halloween demo. All right, hello students. Welcome back to our Halloween demos. So I'm going to show you a polymerization reaction. So this would be something that you're familiar with, like styrofoam, or if you've ever had to spray that kind of foamy insulation into cracks in your basement. And so first I'm going to pour a solution of monomers and dimers. And so if you can guess, I'm just going to eyeball this quick. A monomer is a single unit, whereas a dimer is 2 for di. So I'm going to pour that in there, and I'm going to add a little bit of this food coloring. And now I'm going to get my other solution so that we can get these polymers going. And now I'm going to mix this. And so what's happening as I'm mixing this, I'm causing this to react. And the important thing is, as this is reacting, we are going to trap a gas, carbon dioxide specifically. And then once that happens, it'll increase in volume. And that's why I'm stirring here to get this reaction to go and the polymerization to happen. And then eventually what's going to happen is you should see this harden, and that's when we have some cross-linking going on. And so the polymers react, they cross-link together, and it hardens the structure. In here, it's a nice green color, and my cup is orange, so we should be creating, you know, the effect of a pumpkin. All right, so it's starting to rise. We should see it come out the top very soon. And so right now, if you can see, like on my stir, it's like kind of like jelly looking, and it's rising up. It's almost there. You will see it soon. It should be coming to the top. And so we have that gas. It's a little bit bubbly, you can see, so that carbon dioxide gas is trapped in there, causing the volume to expand. This is slightly warm on the outside, so it's another exothermic reaction. And once this comes up to the top and stops rising, it'll harden. So here it comes. Ah, you can see it. And so once this hardens, it'll be really hard, like a styrofoam cup. It'll be very, very hard. And that's all of that cross-linking going on. And so the polymers become very rigid.
Hi, I'm Miss McDonough. I'm one of the other chemistry teachers here at Conestoga, and I'm going to be demonstrating some light type reactions for you guys. So the first reaction that you're going to see is a chemiluminescence reaction. And when a chemiluminescence reaction occurs, the energy to emit light comes from chemical energy. So we're going to see a light that's produced, but there's no heat that is produced in that reaction. So here I just have a beaker of water, and I'm going to add a chemical that's labeled as instant light. And in this instant light, this contains luminol, and luminol is going, when I add it to the water, it's going to have an oxidation reaction, and that's where we'll see that light being produced. Just a little bit of this. Just need to stir it up to see that chemiluminescent effect. Starting to occur there. And this light is emitted during a change from the activated state to the ground state. So that's how we see this light being produced. You should see a nice bright blue color. Starting to change there. See just a little bit of light being produced. No heat is being produced here, just the light. And you may have heard of luminol before. It's typically used at crime scenes to detect trace amounts of blood. So the luminol actually reacts with iron in blood, which is another oxidation reaction to form that glowing effect. Now in our other setup that we have here, this setup with the fish tank, this is actually fluorescence that is occurring. So here, fluorescent substances absorb UV light and then re-emit that light, which we can see here. So we have the black light here, which produces that UV light, and inside this fish tank is just water with some B50 vitamin. So if we kind of mix that around here, we can stir that up and sort of see the fluorescence happening. And if I get just a little on my hands, you may even see my hand glow a little as well. The creepy witch skin. All right, so those are our two light reactions.
Four witches made quite a commotion when I invited them to create a potion. Into 4 glasses went the magic brew. And into a rage the first witch flew.
There's no magic in this drink. To cast a spell, it must be pink.
The pink is here. Pour the brew in. The color will appear.
We need more!
Now there are 2 glasses of pink, but no one asked me what I think. I will invoke my powers to make it clear. Be gone, pink. Watch it disappear.
And so you see, your Halloween treat today is a little chemistry.
Hello, this is Dr. Mahelsik, and I'm here to show you a demonstration that actually is an acid-base reaction. So if you take a look at this paper, it's a nice yellow color. Okay, so let's see what happens when we take the paper and we turn it, when we treat it with a base. We have Windex here, which is a base, has ammonia in it. So when I spray this with a base, it turns this nice red color, because the yellow pigment in the paper is reacting with the base. So that acid-base indicator goes between orange and red. Well, let's see what's on this paper. Looks perfectly blank. Oh, and it's upside down. And you can see that the mysterious message, Happy Halloween, appears. Okay, so how did I do that? Well, all I did was take something that blocked the spray. I took a wax crayon and I wrote on this. Now, when you come to intermolecular forces, you're going to learn about things that are polar and things that are nonpolar. Wax is very nonpolar. Water, basic solution, is very polar. So the nonpolar wax blocks the polar water so that the spray, the ammonia spray, cannot penetrate there. And that's why I see the orange letters on the red background.
Hi students, Mrs. Roberts here again. For our grand finale, we're going to do our fire-breathing pumpkin. Now, before I turn the lights off, I want to tell you a little bit about what I'm working with here. So we have our pumpkin, obviously, and we have a tiny little candle inside of there. Now, what I'm going to be using is something called lycopodium powder. And lycopodium powder is a very fine yellow powder. Maybe a little tricky to see, but you can see here, whoops, you can see there a little bit more what it looks like. Now, what is lycopodium powder? Lycopodium powder is basically a moss spore. So it's a very, very fine powder. Now, is this flammable on its own? No, it is not typically flammable on its own, but I'll explain why we see this happen in just a moment. So, my able-bodied assistant, Mr. Roberts, is going to shut the lights off momentarily here, and we'll get started with our fire-breathing pumpkin. Thank you, Mr. Roberts. Okay, so we have our pumpkin here. We have our nice little jack-o'-lantern. So let's see if we can get this pumpkin to breathe some fire. I'll do it a couple times and we'll see what we can do. Bring it up. Oh, that one's done. Oh, there's a good one. We'll do a couple more times, and then we'll figure out what the heck is going on here. All right, I'll do one in slow-mo for our final one here. Nice. All right, so let's figure out what the heck was going on there. Go ahead, Mr. Roberts. Okay, so remember I said this powder is not typically flammable on its own, but we clearly just saw some fire, so what the heck is going on here? Well, what we have going on is this powder, remember I said, is very, very fine, meaning when it is dispersed in the air, each of those tiny little particles is surrounded by oxygen. And when I have something that is a very, very small spore, spores are essentially like little fuel supplies for growing plants. So now we basically have this tiny little fuel supply surrounded by oxygen, and if you're thinking ahead, if we have fuel and oxygen together, that means we're gonna get some flammability going on. We basically have combustion happening. So that's why this was happening. Now notice, as soon as the oxygen around each of these particles was essentially used up, that fire went out, right? I don't have just balls of fire all over my room now. So it is sort of a temporary ignition. Now, this has some very real life applications that we need to be concerned with if you're in certain situations. So anywhere where you would have a very, very fine powder dispersed and you could potentially have a spark, that can cause some serious problems. So some places like sawmills, grain silos, like paper factories, anywhere where you're going to have very, very small particulates dispersed in the air and have the potential for a spark from machinery or someone smoking or something like that, you can actually have entire factories go up, instantly, basically, seemingly, because of just this one spark and this temporary ignition. So there are certainly very real safety concerns that need to be used in places where you need very good ventilation system to prevent these things from happening. So I hope you enjoyed all of our demos today, and I hope you have a wonderful Halloween.